everyone. We are going to start this second module with respect to what we saw in previous session. So, I will continue with the earlier point even, like where we discussed about different instructions which were translated to object code. Accordingly, we have seen that there are some particular changes that are happening from instruction to instruction. So, it definitely can tell us what instructions are used and what kind of operands are there. So, in today's session as well, I am going to cover a few more instructions what we earlier have seen. So, this is what when we stopped in previous session, like when we concluded previous session, this was the code which we exactly addressed upon. So, these are all the instructions which exactly are containing say immediate data, and if you see this immediate data in this case is 10. Now, it is written as 0A and all this consecutive zeros. So, let me make some change into the code and we will talk about the same thing. Emacs test dot asm. Now, I will remove these all and I will take some instructions even with some data like 0x 1 2 3 4 5 6 7 8, move ebx comma 0x 1 2 3 4 5 6 7 8. So, let us see how this code gets translated. So, nasm dash f elf 32 test dot asm dash l, again I will take p4 dot lst. So, let us see contents of this p4 dot lst. If you see here, this data, the data that we passed was 1 2 3 4 5 6 7 8. So, ultimately it covered 4 bytes completely. Now, the data in the order the data was given was 1 2 3 4 5 6 7 8, and if you really see over here what is the translation that we got, it is taking the byte, the last byte would be picked and would be put as a first byte, and whichever was the first byte would be put towards the last. Fine. For example, here if we see 7 8, then 5 6, then 3 4, then 1 2. Same case was here. So, what exactly this is? So, for that purpose, let us try to understand what this is. We are talking about a particular formatting used by most of these machines. Right now, currently we are talking about Intel architecture, and in Intel, like we do see that there are two different kinds of mechanism proposed, rather Little Indian and Big Indian. These are the two ways where these two ways would be used for stating or maybe storing the multi-byte data. It could be more than a byte for a while. So, for example, integer, float and so on. Integer, in few cases we saw it was 2 byte, then when Linux came at that time, or even GCC had GCC compiler supported 4 bytes. Float even earlier had 4, then 8 and so on. So, ultimately what are the data that we are passing, how exactly this data should be stored. So, as an example, I have taken over here this same immediate value that I took in the earlier program 1 2 3 4 5 6 7 8. Now, when we talk about this Little Indian, Big Indian, in Little Indian scheme, the last byte of binary representation of the more than 1 byte data would be picked first, okay, and we will follow the similar order, whatever the order that is there, like 1 2 3 4 5 6 7 8. So, 1 2 will go towards the end and 7 8 will come as the first element. So, in binary, suppose if I write this 1 2 3 4 5 6 7 8, then this is the representation for it 1, then this 2 3 4 5 6 7 8 in in terms of nibbles I represented it. So, Big Indian notation will store this number as it is. But whatever the translation that we saw, which was applied internally by NASM, NASM actually makes use of, or even the standard assembler GAS also makes use of this scheme, rather the Little Indian notation, where Little Indian notation, if you see, this was the last byte, this will be put as a first, okay. Then subsequently this was the last byte 1, it will be put as a second byte and so on. So, whatever the first byte would be there, it would be put as a last byte. So, about these rather even we are going to discuss further more, because as and when we move further we will be requiring some more information about this particular formatting mechanisms used internally. Okay, so in continuation to what earlier we have seen, we said there would be opcode. As earlier I stated that opcode would be compulsory, it would be written, it would be either 1 byte, 2 byte or a 3 byte. Okay. Then there would be a mod rm, it is if required, like in manual only it said if required. Now when we say if required, ultimately it means what, like the instruction only will while we are translating those instruction will only tell us whether the rm byte would be required or not. Even if we see this scale index byte, okay, scale index base register SIB. So in such a case as well, if required is written. Displacement, even whenever you have some memory representation or if you are referring to some variable defined in data section, then ultimately this displacement will come into picture, as well as this immediate data which would be available. So even in the manual only when they discussed about, the Intel people discussed about this how many bytes would be required. So displacement can be 1, 2 or 4 byte. In the same way, like immediate data would be either 1 to 4 byte. Now one important thing that we will see in today's session is what, so what when we talked about move instruction, we saw that it took completely 4 bytes. So in this case, like to store this data, we can see that this data would be translated into number of bytes to be 4. In the earlier example, even when we took this code rather, we gave only value as 10, which can be fitted into a byte, but it ultimately took 4 bytes to represent it because of the Indian notation, little Indian notation. Now if I change this code, say for example to something like by changing few instructions, so I will replace, I will take these both instructions over there and I will replace that move by add. So let us take this add as an instruction. So I am adding immediate value to EX as well as EBX. Now if we save and translate this rather, let us check that P4 LST. Now let us try to understand what exactly is happening. In this case, if we see add and move instruction, the last part, the latter part rather, with respect to the immediate data would be same, like 7, 8, 5, 6, 3, 4, 1, 2, same case would be here, same case would be here and so on. Then where is the change is? So in this case, when the number of bytes required to store this immediate data is 4, it is quite good to see even the same representation used across. But if the data changes, say for example now we took this 1, 2, 3, 4, instead of the 3, 4, 6, 7, 8, let me take only 10 or 12 maybe as an hex value. So I am deleting all of them altogether and let us again apply the translation. So if we see the same P4, now see the drastic change that had happened. With move, if you see, this 12 would be put as a 12 value, because this 12 is a hex value, it is not a decimal value. So that is why it put it as it is, so 12. Even the same case with move, one may see over here that 4 bytes are picked. But if we jump to this add, now these two add instructions which were added by us. So one may see over here that this 12 required to store hex value 12, you definitely will be requiring only 1 byte, and that is what is happening over here. So only 1 byte is picked to represent this, and that is the reason why if we see here in the manual, even they said it may take 1 byte, 2 byte or 4 byte to store the data. Okay, so this is what the kind of treatment given with respect to immediate data. So as one can see over here, in we are requiring either 1, 2 or 4 byte. There is no thing defined here for number of bytes to be 3 for immediate as well as displacement. Now on the similar line, what I will do is I will add some thing over here, like saying that add EAX comma A, add EBX comma A. Now A here, if we see, we have declared that A over here as a string. So okay, we will take B even over here, which is in earlier data declaration, data section rather, we had B defined as 10 and 20 considering two values. So, let me translate this code again and let us see what are the content shown. Now, one may see here that this B is represented by some square brackets. Fine. Now, let us go to the translation that had happened in the top half, like starting from line number 1. If we see, what we discussed earlier was this A would be converted, this each character would be converted to ASCII and then its hex equivalent would be put over here. So, this is where A declaration is finishing, and this is what we have B. Now, if we compute this number of characters over here or length over here, it definitely is 11, is hex 11, okay, or decimal 11. So, let us see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 and so on. So, after F if we see rather this 10 and 0 is put over here, which is /n and /0. After that, when number of characters are finished, then we do see that this is the address given, means next address, consecutive address would be given for this B, and this B is kept as the values that are here are 10 and 20. So, 10 represented in hex would be 0A, and one may see over here it is taking 4 bytes to store, 20 hex equivalent would be 14. So, this even is taking 4 bytes. Now, the address, this is a translation time address given right now for here. So, one may see here that it is 12. So, same is represented here with the little Indian notation. So, whenever we are referring to B or A, okay, accordingly the address would be picked. So, if we are referring to A, though it may you may see here that it is taking 2 lines over here to represent this contents of A, but ultimately this A would be represented by this address only 000. So, if I am referring to A in this case, then it would be in square bracket, I will be able to see that it would be represented as 000. Now, let us see this remaining translation. So, the way that we saw this add EAX, the opcode given was 83, add EBX, the opcode given was 83, C0 and C3 are the mod RM byte that was taken. So, this opcode as well as mod RM was involved over there in these two translation. But when we see this particular data which was passed as an immediate value, so one may see here this immediate component which is added into immediate data instruction format is added there, and as stated there, as it took only 1 byte for add, but same case for move it took 4 bytes. Let us go further with respect to this add EX comma B and add EBX comma B, though these instructions we are not considering some senseful operation over here, but it is only to understand what the translation process is. One may see here like add EAX, when we put it took only a complete opcode, no mod RM involved. But if we talk about this add EBX, one may easily see that it actually took this 81. And this 81 was opcode and C3 was mod RM byte which was picked over there to represent this instruction, and this B which is a memory rather, because why memory, we have defined this into data section, and this is the address which is picked or taken to translate it. So, this B would be represented as this address and so on. So, let us try to find out what exactly happens over there. So, let me go to add instruction, so that we easily can understand what the code is. So, let us take say for example, this instruction we had 83 as an opcode. So, if you see over here, this is what it is like 83 and this one immediate 8 RM32. So, if your data is it can be fitted into 8 bits, that means a byte, then it will take 83. Now, if it is going beyond, now even one may see here that when we do talk about this 83 was taken for these both instructions where register is involved, fine, and this C0 C3 as early in referring to earlier session we had, this C0 and C3 came because of the registers that we have used over there in through the mod RM byte, fine. Now, with respect to this add EAX, if we see the opcode taken here is 05, fine. So, if we see 0 5 over here, 0 5 can be seen here, add Ex comma immediate 32 or add Ax comma immediate 16. Now, in both cases, like as whenever you are using a register internally while writing the code that we wrote, this code is using Ex as a register. So, that is the reason why this opcode 05 is picked, fine. So, for Ex separate treatment is given in add. Now, if we see the same case with respect to this add Ebx. Now, add Ebx, if you see, this is a register other than Ex. So, we have to identify now some instruction where there would be register memory involved as well as immediate 32 would be added. So, the opcode that was taken there was 81. So, if we see this 81, let us see this 81. So, this is the representation that we have, add RM32, see it is referring to register or memory 32 and an immediate. Now, we even have some one section in NASM where we easily can write something as a variable which is defined but not initialized. So, it goes to BSS. So, it is referred as block starting with symbol. So, let me define a variable called C, then I will declare it as a double. Okay. Now, what are the value that is there with Ex, say for example, I will move it to move d word of C comma Eax, or let us first take this 0x12. On the similar line, what I will do, I will add instruction over there even. So, here we are trying to identify what is the treatment given when register is an operand or a memory is an operand. So, instead of move, now I will take here as add. So, let us try to translate this. So, we got the code. Now, let us see this code. So, move d word C. So, we got C7. Okay. Now, you may see here that you have now more entries over there like 0000, which is now referring to this BSS section. One may see here that 00 is there with data section, 000 is there for BSS and as well as 000 is there for text section. So, in object code one easily can identify, not here maybe, but the exactly ELF32 file, we will see that there would be segment prefix added with respect to this data, this reference. Now, what are the address that we are referring to? So, if I am referring to address which is 000 from text section, then there would be reference or maybe prefix added for text section or code section. Same case would be for BSS and data as well. So, if let us take this example. Now, we saw this 83 opcode used for add when we added a register. So, for example, add Ex comma 0x12. So, one may see here 83 C0. Now, C0 was because of this EBX. Now, though this 83 is there, and if we see add d word C, 83 is here as well. Then how this 05 came? Okay. Even if we see, we referred to a variable C which was declared into BSS, correct. So, now the instruction what are the instruction translated we have now, what are the instruction that we got after translation? It should refer to the immediate data as well as the address used there, because we are referring to some memory content and we wanted to move this immediate data to that variable. So, the instruction should contain both the things. So, that is why now this C is represented as an address. So, that is why this is displacement, okay, what we saw into instruction format. This would be displacement and this 12 would be the immediate data that we had. So, if I remove this immediate data this displacement from here, then it will be similar to somewhat what we saw earlier with this add instruction when we added directly this 12 to the register. Now, let us try to find out what this 05 corresponds to. Now, there is nothing called like we do not have right now the register used here. So, but mod RM byte came into picture. So, if I write this 05 maybe in the file, I have 05. So, let me write this 05. So, what 0000, then 0101, fine. So, if I now divide this in terms of 3 bits and 2 bits, so I got this, fine. So, let me take another example over here so that it will be clear for us. So, instead of this P4, now I will take some other thing x1. So, we had d word of C. So, let us say move d word of B comma 0x12. We will take even add here, fine. So, let us try to again generate the file. So, we got p4.lst. Now, you may see over here the difference. Now, this, if you see, the instruction looks same, only what are the translation that we got here. We are referring here some variable which is different than this one, correct. So, one of the variable is from BSS and one of the variable is from data section, and data, what are the immediate data that we have forwarded or moved to the register to the variable as an immediate value, it is same across both the instructions. So, this address now is referring to the particular address which can be seen over here. So, as the variable B is used, one may see here that this 12 is there, this 12 is represented over here. So, only thing is it is written in Indian notation, little Indian notation. Now, you may see here this 83 is taken as a constant thing, though you are referring to some variable which is from different section. So, now as there is no register involved, so with reference to the if we refer the earlier session that we had, we said that this 000 would be representing EAX and 101 would be referring to something else. Now, how exactly are we going to differentiate that what kind of instruction it is? I mean to say, like whether the instruction is containing register or whether the instruction is containing immediate data, and that is what here makes the difference. So, when we took this 83 over here and 83 over here, even same both the cases, 83 when having C0, C3 and so on, if I replace, like if I add over here all registers, you will see some consistency applied over there. So, what I will do is I will add all registers over here, control K, Y. So, this is ECX, we will make changes into the register. So, this is our ECX, EDX, this is ESP, EBP, okay, and this is ESI. So, let us translate this one now. So, let us check the code which we got. Now, if you see this C0, C1, C0, C3, C1, C2 as the register, if we recall the register at the order, it was EX, ECX, EDX, EBX, ESP, EBP, ESI, EDI, and that is what the order is taken. Like if you see over here, for ESI it is C6. So, ultimately the EDI would be the last register. So, whenever we are picking these ones, actually this design is intelligently given with respect to the translation process. If we go to that particular page 40 where that mod RM 32 bit representation is there. So, let us see this 000. Okay. For the register, what are the code that was taken, in this case is C0. Now, let us try to find out where is this C0. Fine. So, C0, C1, C2, C3 is here. Okay. So, mod in this case is 1 1. So, C0, C1, C2, C3 and so on. So, we got this one, fine. Now, this tells us that here you have something called as a memory, okay, because one may see here, though it is taken through EAX, but even this mod is given for this particular RM byte. So, these would be taken as RM and the register number would be picked from here. So, register number would be picked from here rather, like when we do talk about the register numbers ultimately. So, in such a case, like if I write this C0, C3, C1, here if I try to write this C0, C3, C1 in my binary notation will end up like this. Now, the hex representation that I got was C0. Okay, so C means 11, 12. So, 8 4 0 0 and this 0 0 0 0. So, now if I divide this in terms of this, so in this case mod became 1 1, fine. So, it is true for all registers which we can see over here. So, for all instructions which are added here in this code rather, this C is constant. So, this itself is telling us that the mod which was used over here is 1 1. Suddenly if we see the other case, for example this one with 83, earlier we had C0 to C7 for all the registers, but when we took some variables it became suddenly 05 05. Now let us see what exactly this 05 corresponds to. So let us try to translate this 05. So we will write 05. So 05 0 0 0 0 and we got 0 1 0 1. So this 0 1 0 1 0 1. Now if I see over here mod 0 0 and when I see the lower bits are comprising to 1 0 1, then this itself tells us that there is a instruction which is moving some immediate data to memory, fine. Now if we see same case when we had a register involved over there, the mod was taken as 1 1. So when your register is there, there would be 1 1, and when your memory is referred over there, then it would be the code, as we said, constant code, the number of bits that are taken are 101, fine. So this 12 and so they would be similar, like whatever the way that this 12 is stored, 12 would be same. Now with respect to this 81C3 and this, why they might have given separate treatment to this EAX, as EAX is referred to be an accumulator. So most of the times this EAX would be playing a key role into whole process of translation. Even at the time of execution, it should store the return value, as well as it should store the system call number and so on. So as it is doing multiple things, so they specifically made a difference because they have to optimize this table which we saw over here into this PDF file. This is a 32 by 32 representation, like what are the code that we got here, which this mod IRM corresponds to these codes only. So appropriately the mod would be picked and the registers would be automatically identified. So if I am been given say the object code, I can easily find out what possible could be the memory, though I may not be able to really tell whether right now at least whether this is a variable from data section or BSS section, but I definitely can tell that this is variable defined and at what address it is stored, or it is what address is given to it. So the way that we saw here, that it started from 0 0 0, ultimately the address started from 0 0 0 and it ended with the last value that we saw over here in this case, correct. So this is these are the two cases that we identified right now, where we had add and we are even consider move instruction, where we passed immediate data. Now if I use instead of add, if I use move, one may see over here this C7 is picked. Okay. Now if I try to differentiate between this add and move, instead of only talking about this C7 part, this is opcode taken in this case. Now here it is C7, here it is 83. Now this 83 and C7, if we remove them, rest of the things are same. Okay. Only difference again is how you represent this 12. As we earlier stated that whenever you have data to be moved as an immediate value to some register, or even the memory, every time this it will take 4 bytes and it will make use of little Indian notation to store to show the representation, store the values accordingly. But same case would not be true for add instruction, as one can see over here that in add instruction this 12 would be stored in with respect to number of bytes required to store it. So in this case, as 12 requires only 1 byte, so 12 is shown over there, fine. So now I will take one more example with this case and then let us see how the translation goes. So let me make the change here even in the code. So now instead of this, I will put it here as say XOR EX comma EX, XOR EBX comma EBX. Now specifically I am taking some XOR instruction. here I am taking OR instruction, and maybe here we will take AND instruction, and let us see, do we see some change over there in terms of the translation that would be given. So, we got P4.lst. Now, see over here XOR EX EBX. So, again one may see here, as the operands are both of them are register to register. So, definitely one may see that the mod would be taken as 1 1, because whenever you see anything starting in if we refer to this anything, if mod RM byte starts with C, the byte if it starts with C or if it starts with F, between this every time you will be saying that only registers are included into the as an operand in the instruction, fine. So, referring to this code C0 and DB, which if we write in binary, one can easily identify which registers are used. This 31 would be used for XOR. So, if we see even the other instruction like OR EBX, in this case again there is a mod RM included CB. Now, with respect to AND, one may see even E1 and CB. CB, as we already even see over here, that CB would be somewhere here. Okay. So, that number would be common in such a case even with respect to E1 as well. Now, we have AND ECX. So, this would be opcode, 83 would be opcode, and E1 and CB is referring to them. Now, are we missing something? Like for example, whatever the earlier code that we saw even 83 over there, fine, and in this case also we saw 83. Now, we should know now how exactly we are going to differentiate these instructions altogether, whether it is move, whether it is add, because multiple times it will be making mistakes with respect to identifying the original instructions, fine. So, in next session we will be talking more about few more internal details of how exactly to differentiate these codes when the codes are given to us at the starting point, fine. Thank you.